Thank you everyone for joining us today and welcome to GOWIN's webinar series. Today's discussion is DesignStart FPGA 201, Designing with Arm Cortex M3 and GOWIN's FPGAs. My name is Scott Casper with GOWIN and I'll be your moderator. Our speaker today is David Grugett with GOWIN Semiconductor. Please feel free to send us questions via the question or chat button throughout the presentation. We will answer them at the end. Our agenda for today will be as follows: speaker biography, introduction to GOWIN Semiconductor, DesignStart FPGA, designing an Arm Cortex M3 soft CPU into GOWIN FPGAs, and we'll finish with questions and answers. A bit about our speaker. David Grugett is the Senior FAE Manager Americas for GOWIN Semiconductor, focused on implementation of solutions for programmable technologies. He has over a decade of FPGA systems architecture and implementation experience in areas including ASIC prototyping, interfacing, bridging, and edge connectivity. Mr. Grugett received his Bachelor of Science in Electronics Engineering Technology from DeVry University. Now a brief overview of GOWIN Semiconductor. GOWIN was founded in 2014. Our executive headquarters is located in San Jose, California, and our operational headquarters is located in Guangzhou, China. We have over 160 people employed in R&D, engineering, and administration. We serve the low to mid-range density markets for FPGA needs from 1K LUTs to 100K LUTs. We offer two product families, our Little B flash-based FPGAs and our Aurora, our SRAM-based FPGAs. Little B's low-density products are targeted for mobile, consumer, and IoT applications, such as bridging and multiplexing. They are also used in industrial, commercial, and server applications for CPLD replacement and power or platform management. The Aurora mid-density products are targeted for communication, industrial, and automotive applications with high-speed interfacing and I/O expansion needs. GOWIN is known as the innovative FPGA company. Some of the key differentiating features are hardened embedded MCU cores, embedded PSRAM, DRAM, and flash memory up to 16 megabytes, a vast offering of I/O interfaces, low power operation targeting 28 microwatts always on, embedded security offering root of trust capability, authentication, encryption and decryption, and secure cloud connectivity, RF capabilities, and AI and machine learning solutions. For more information about GOWIN and our latest innovative products, please visit us at gowinsemi.com. At this time, I'd like to turn it over to David for our main presentation.
Thank you, Scott. And hello, I'm David Grugett. Welcome to GOWIN's ARM DesignStart FPGA webinar. DesignStart is a no-cost, no-license, royalty-free Cortex-M IP program. The Cortex-M is optimized for FPGAs with small area and control logic. GOWIN and ARM want to help you differentiate your products, reduce your costs, shorten your development times. And with DesignStart FPGA, this offers a complete, fast, easy, and instant way to simply integrate a Cortex-M solution onto a GOWIN Micro SoC FPGA. You don't know where you're going until you know where you've been. And 2 years ago, we were at a Cortex M3 hard IP, and we put them into two of our Little B FPGAs. So this hardened MCU had some peripherals and timers, UARTs, watchdog, but to add on more peripherals in the FPGA fabric, we had the AHB Bus allow for I2C, SPI, and that's about all that you could add on with the amount of logic that was available, 2,000 to 4,000 logic elements. So some of our customers wanted more logic. So we came out with the soft M3, but the same Little B family offers some other hardcore IP, which includes a USB 2.5 and an A to D converter. So we still have families and applications for the 2C and 4C devices. But the soft Arm Cortex M3 is available for our Aurora family, which is our bigger density devices that Scott was talking about. And it's all FPGA. There's no hard ASIC IP in this application. In this case, it's the microcontroller unit with some of the peripherals hooked up to the AHB bus, the high-speed bus, and then the peripheral bus for some of the slower peripherals. But a basic MCU in an FPGA would take about 17,000 logic elements or LUTs. And if you put more peripherals on there, all the peripherals you see here, it'd be about 37,000 logic elements. But still, in an Aurora FPGA with 55,000 logic elements, you've got almost 20,000 logic elements to add on some secret sauce for your application, and maybe some more peripherals to extend the AHB and APB bus. Now, we did offer last year, or release I should say, we still offer it, a Cortex M1 soft core. This one is a small little B type soft core that can fit into maybe a 9,000 logic element little B device if you include some of these peripherals. So this is also an option with more peripherals in a pure soft IP play for our little B as well as the Aurora family. So that's just something that we released last year, and you can use the same development tools that we'll talk about today to do a Cortex M1 or a Cortex M3 design. Speaking of tools, that's part of our ARM DesignStart FPGA program. They're free. They're available for download off our website. We have a DesignStart FPGA splash page that has all the links, or you can go to specifically development tools and download our EDA tools, which are available in both Windows and Linux. To use them, we have a license request online. It's based on your MAC address for your PC or license server, and it's based on a hex value that we can use that to generate a license for you. We'll send it to you. The GOWIN EDA tools also includes the IP core generator, which is where the soft M1 and M3 and the hardened M3 configuration tools are available, along with some of the other peripherals that you can add to your design. The other tool for the software side is our GOWIN MCU Designer. That's the great thing about the ARM ecosystem, is there's lots of free software out there and public domain open source software tools. Although ARM with their Kyle tools, which you have to pay for, is more elaborate. The basic tools that we use, the GOWIN MCU Designer, or GMD for short, includes debuggers and the accessibility to trace cables. There's lots of hardware on the market that can be used with that. So if you download from the DesignStart FPGA website on our page on our website, you can get a user guide as well as the design software, MCU Designer software. The latest version is 1.1. This screenshot shows 1.0, which is why when you do request a GMD license, you have to do it by email. Send it to license@gowinsemi.com along with your MAC address, the same one that you had for your EDA tools for the PC, as well as the version of GMD. So we'll generate a license for 1.0 or 1.1. The last thing you'll need is our softcore design reference design. This includes both the FPGA reference design as well as the C code for the peripherals and the core that you're using, which is the M3 core. Also included in there are documents as well as designs for the Kyle MDK tool and the GOWIN GMD tool. There's no need for a separate IP download for the IP, the M3 IP. It's included in the reference design. But if should you want to modify it, you can modify it in the GOWIN EDA tool through the IP core generator. So the two flows we'll talk about today is the FPGA design flow. Once again, this is very easy to use. It's with our EDA tools. You can add your user design in Verilog or VHDL. But as far as the Cortex M3 IP and the peripherals associated with it, we generate a Verilog file. That flow then goes to our synthesis tool, and that net list that is output from the synthesis goes to place and route. And then the place and route will create a custom bit stream for the device that's targeted, as well as the pin locations for your board. Speaking of the board, our GOWIN development boards are available for known working hardware, and that's where an engineer can start prototyping the FPGA platform that they create, in this case, the Cortex M3. And at the same time, your software engineer could be writing the C code and compiling that and creating a image file, a raw binary image file that can run on the platform that we're about to generate. So this flow is RTL, and this flow is usually C or assembly. The reference design that you downloaded is zipped. So when you unzip it, you'll get a path that's usually in this format. And then you can find the reference design folder has two flows, one for the FPGA, which is what we're about to go into. And the other one is for the software, which we'll get into when we go through the software flow. But if you stay in the FPGA ref design, you'll see we have one targeting our eval board, the DesignStart GW2A55, and it's got the pre-configured GOWIN eMPU M3 design. This design, you can tell by the GOWIN logo, is associated with a GOWIN project file. And when you double click on it, you'll be able to launch our development tool. And if the project doesn't launch, then you can go to File and Open Project and point to that same path that you just launched the GOWIN reference design project for FPGA. The first thing you'll notice is the device that we're targeting, and then the Verilog files that we've already created in the reference design. You'll also see the IP core file, which is this GOWIN eMPU M3.v file that was created in IP core generator. And then you'll also see a constraint file. This constraint file, CST, is for the pins located on the eval board, and it's got the IO types and pin locations associated with that reference design and that specific board. So if you double click on the device, you'll go into more details on the device, which is the part number, the ordering part number, the family, which is the Aurora family, and then the package. In this case, it's a 484 BGA package, and the speed, which we dual mark our parts with the commercial speed grade and the industrial speed grade. The higher the number, the faster the part. So you can see at the lower temperatures of commercial grade, it can run faster, and the higher temperatures of industrial, it'll run one speed grade slower. The voltage for the core is the LV for low voltage, which is 1.2 volts. We do have upper voltage for some of our little b devices, which is 3.3 volts. The number of IO that is in this package that's available, these are all single-ended, but we do have differential pair for LVDS, etc., LVCMOS differential. The LUT or lookup table count is the equivalent to logic elements, 54,720, and part of that would be part of the M3 core that we're going to use in the design, but this is just the total for the device. We have flip-flops, shadow RAM, block RAM, multipliers for multiply accumulate applications, and some clocking features, including analog PLLs and digital delays. The platform used in the GOWIN eMPU reference design is the M3, and so we generated it already in the reference design, but if you wanted to view it to see what the platform looks like, you can go to the Tools pull-down menu, Launch IP Core Generator, and you'll see all the IPs that are available for that specific target device. In this case, anything that's in dark color is available. Anything grayed out can't be used for that device. There's more IP below this soft-core MCU. I just didn't show it on the screen, but you can see a lot of soft IP is available that you can add to your design in those logic elements that you have available for your design. So the reference design creates an IPC file, which is the IP core generator file, that extension. And if we double click on it, we'll see that we've got a pre-configured platform that can be used. And the breakdown of that platform is in 3 sections: the core system itself, MCU core system, the peripheral buses, which connect to the AHB bus, the HighSpeed bus, as well as the peripheral bus, which has some of the slower peripherals. So I'll show you how you can enable each of these sections to create a platform for your application. But in this case, we're going to target the reference design that is used, that's associated with the software code that's going to be written for the reference design. Here's the subsystems in our reference design. We'll have user interrupts. We'll have, of course, the Cortex M3 MPU, Wakeup interrupts, bit banding capability, interrupt request levels, Wakeup lines, number of system or sensors that can maybe wake up a embedded application. Debug, in this case, we'll have full debug. You can turn that off when you do a release code. The debug interface, we could have JTAG or serial wire, depending on how many IOs you have available. And of course, the instruction and data memory size. For the AHB bus, the high-speed bus, we have the general purpose IO enabled, the SpyFlash, and the high-speed bus extension, where you can add on your own secret sauce peripherals in the FPGA fabric. And for the slow peripheral bus, we have some of the typical UARTs and timers and watchdog timers all enabled. So I'll show you how those are easily enabled and configured. So we'll start with the MCU. You get the processor core, the interrupts for Wakeup, and the non-maskable interrupts. We'll configure the memory and the buses. We'll configure the debug, which is the serial wire debug, as well as the JTAG debug. So it's easy to point and click when you click on the processor in the previous block. This right here, actually a lot of these, anything that you click on this block diagram, it's context sensitive. It'll open up this configuration window where you can go in and enable some of these features, like of course the MPU, the Wakeup interrupts, enable the bit banding, and set your interrupt requests. You can have 16 interrupts, and then for the Wakeup, you can have up to 243. So a lot of sensor inputs to wake the controller up from sleep. So once the core is configured, we can go to these, or the basic core, we can go to this debug section. The debug for the software debug is usually the full DWT or data watch point and trace that gives you the capability to do single step or run it to a breakpoint, and then you could see what happened before the breakpoint and after the breakpoint. The trace level is the ITM, the instrumentation trace macrocell, as well as the data watch point trace. The embedded trace macrocell isn't needed, so we didn't configure for that. The more trace and debug that you do, the more lookup tables it'll take in the FPGA. So that's the other thing you got to look out for. It'll also use some of the memory that's on the device, not used memory blocks. But if you use a download tracer cable, it'll have memory on there. So that would be another way to go for debug. So there's lots of options there with debug capabilities, including the interface. If you don't have very many I/O pins, maybe you want to do a serial wire, which can help you debug your code, or you could do serial wire and a JTAG interface. Next section is the memory. For instruction memory, this is where your compiled C code is stored and run. It's in the block RAMs of the device. The hardcore was limited to 64 kbytes because that's all the devices that we targeted had. So we've expanded the amount of instruction that you can do in the softcore up to double 128 kbytes. The actual initialization path of your compiled C code can be pointed to, and so that will allow you to run and debug your code. The data memory is also the same scenario where you can put in block memory, embedded block RAM, twice as much, 128 kbytes, and you can do this in the Aurora family with their embedded block RAMs. And once again, both the instruction and data memory can be stored off chip in a SpyFlash memory. And then on power up, the FPGA will be configured with the platform that we're creating. And then once the controller is running, it'll go fetch the instructions from the SpyFlash onto the SRAM. So it'll be actually running the instructions from SRAM, and the data will be running from SRAM too. So the HighSpeed interface, this is a bus that offers like general purpose I/O. So in this case, we want to enable that to drive some LEDs on our reference design. Also the SpyFlash controller. This will allow memory to be looked at from on power up from the MCU. And then the AHB 2 extension is for allowing more high-speed peripherals to be added to your design. So we'll do the same kind of enablement that we did for the microcontroller. It's just click and it appears. In this case, the general purpose I/O is a 16-bit interface. So we have 16 signals that we can use to go to the FPGA fabric, or it's already in the FPGA fabric, but go to more specifically the I/O blocks. And we can have those signals coming in to the design. In this case, we'll have outputs driving LEDs. The SpyFlash is interfacing to the off-chip SpyFlash memory that will store the compiled code. It could be also used for some constants you might have in a design. So the SpyFlash that we use on a reference design is 64 megabits. So it could be used for configuring the FPGA, storing the boot code, and then storing some constants that you might have in your application. You can see once you enable it, we'll get the output, the input, chip select, and the clock signals. The AHB bus is where you can add on more peripherals to your design that need the high-speed clocking. We base all of our peripherals on an address mapping. So the address mapping for the peripheral bus was 5100, and for the AHB bus it starts at 51 or 5200. So you can add those to your design as needed. All the other peripherals have pre-existing address mapping addresses, and we'll see those when we go to the software side, and then the software will be able to access these peripherals based on their address. So when comparing the usage of the APB and the AHB bus, the APB is usually a simpler bus. It's lower speed. The AHB doesn't need pipelining. Or I'm sorry, the APB doesn't need pipelining. The AHB usually is pipelined. This is usually optimized for reduced interface complexity and minimal power consumption for some of the peripherals. So things like the UARTs and the Watchdog and I-squared C masters and SPI, and any kind of extension that you might have. You can see some of these are available to real-time clocks and SD card readers. We're just not using them in our design. So once we enable them, they turn green. So the UARTs, there's a couple of them, can run at 920 kbits. Once you enable them, you can see the UART 0 and 1 receive and transmit signals. So those are good for some communication applications. Timers, these are synchronized standard timers. They're loadable, so you can count down from whatever address or counter value you put in there, and those are good for embedded applications. The Watchdog timer has more specificity to the application code monitoring. If your subroutines get locked up and they don't tickle the clock as or the dog, then pet the dog, then it will reset an interrupt for you to go do some kind of routine to get out of this lockup. So Watchdog timers are a good application, they're peripheral to have on embedded applications. The I2C is still available. We use that for a lot of sensors that are out there since it's only 2 pins, clock and data. So you can have multiple slave addresses with this master and then have multiple sensors out there. And this could be for the data path for the sensors. You can use the Wakeup interrupt for if a sensor needs to wake up the controller, it senses something that needs to be looked at. So both the I2C and the Spymasters can be used for memory or sensors that are out there on your application, your embedded application. Once again, these are based on memory addresses. So to talk to the Spymaster, you would talk to it through the AHB Bus, and then that AHB Bus would talk to the I/O pins for the input and the output signals, as well as the clock and chip select. And just like on the AHB Bus, you can extend it to add on some slow speed peripherals. Once you do that, that address will start at 5200, and then you could add that onto your software design. And also the actual Verilog for your secret peripheral sauce can be put into the FPGA design. So once we've enabled the microcontroller core and all of its memory and debug capabilities, and we've done the same with the HighSpeed bus, the AHB bus, and the peripheral bus, then we click OK and we generate a few files. The files would include the IPC file that we opened this up with to look at. We can use that to generate other platforms, to add things or delete peripherals needed. It will also generate a Verilog file. The Verilog file will allow you to instantiate the top level. The top level will have the source code for the microcontroller as well as the peripherals. And that's this file here, the .v file. The template is your top level file that has the way to instantiate the I/O pins to these cores that are in the reference design. We've got clocking, the PLLs that are available on the 2A55. We have multipliers and decoders in the design based on the high-speed bus and the peripheral bus. Another file that's included that is specific to this device on the dev kit board is our constraint file. The constraint file was generated when we went to the process tab, the next level. But in this case, it's used specifically for our eval board, and it tells you which pins to use and what I/O types to use. So to go to the process tab, you just click over from the design tab, which shows all the source code. And then you can synthesize using our GOWIN synthesis tool. And once you create that net list, then you'll be able to go to the floor planner and do a couple of things. You can put constraints for the I/O locations and the I/O types. You can also do a timing constraint for any clocks and what kind of timing requirements are for your peripherals. You can also create a hierarchy, and that hierarchy will show that the wrapper was the template, was the top level file, and then all the sub files in your system. So it will take the synthesis tool will take all of those source RTL files, and it will synthesize it to create a net list. And once that net list is created, you'll get a report, and it'll tell you, this pull down window will show you the resources of how many lookup tables were needed, IOs that are needed, and what kind of memory utilization, etc., are needed. So all of those sections are here in the timing and resource for just synthesis. So this is before we place and routed the design, which is the next step. So when we go to place and route, we'll take that synthesis net list and generate a bit stream, and that bit stream will be reflective of the source code in the design, the constraint file in the design, and the timing in the design constraints. So all of that should be reported in our timing and analysis report, our port and PID report. And power. Power is an issue with a lot of design. So depending on how you're clocking your design, would be how much power is being drawn and activity factor. So this is just a kind of worst case power analysis report, but we create files that you can use in our GOWIN power analysis that can help you optimize your power, maybe recommend a heat sink or get some airflow on your design. Those scenarios are what if scenarios to help you reduce your power. We break up power into IO and memory and PLL clocking, etc. So we can give you a very robust reporting on your design, kind of as if it was an ASIC. The other output file is an SDF file. It's a standard delay format file, and that will allow synthesis or simulation tools such as ModelSim or ActiveHDL, etc., Mentor graphics tools, Cadence tools, to simulate the design for timing. And so you get the actual routing between point A and point B in your design through the SDF files. And if you don't get the green check mark here, we've got ways to help you debug your tool, your design in this tool. So we can use GOWIN Analyzer Oscilloscope to go in and probe some signals. Maybe you can see where a routing delay is long because of the routing, so you can go in and change that. But the key thing is that there's lots of tools for synthesis, and place and route or feedback reports to help you debug the design along the way. Since the core has already been pre-simulated and verified, you shouldn't have any problems. Usually the issues come up when you have added peripherals that aren't included with our peripheral library, and just some basic things for clocking maybe, or EBR usage. So those are things that we can help debug in your design. The other thing that comes out of place and route is your FS file. It's your file stream. And that file can be used to program the device. The device can be programmed, in this case, the 2855 on a dev board. And we have the ability to use the USB port on a PC, let's say, and go out and enumerate how many FPGA devices are out there. With a dev kit, you've got one device out there. It's the 2855. And you can target the operation to program the SRAM. In this case, the Aurora has just SRAM. If it was a little b device, you could program the flash on the little b. But in this case, we've got flash external on the eval board that you can, once you've debugged your SRAM, then you can copy that to the SpyFlash, and it'll be a ability to cycle power and have that platform that we just created, the FS file, loaded into the FPGA on power up. The FS file will have a unique checksum, as well as the user code that you can put in there to default to 0. If you have a rev level of your design, you could put that in there. And then the ID code is for the device, specifically the Aurora 2A55 device. And so when you click the program button, in this case, it'll program the eval board. It'll do that through the USB download cable. That will communicate to the FTDI and JTAG to USB to JTAG conversion on this chip. The JTAG on our device can program the SRAM, and then once you've verified your design works in the FPGA and you want to store it in non-volatile memory, we've got the SpyFlash that's connected to the serial, the Spy master port on the device to configure through Spymastering loading. The JTAG can be used at any time to program it, or the Spymaster. You just select the mode selection pins for whether you want to go from the JTAG or the Spy memory. The device also on this board has a lot of I/O, so you could use some MIPI interfaces or CSI interfaces, SD card. We've got some differential singles for maybe DVI inputs, some general purpose I/O for going to some sensors. We have the LEDs that part of our reference design is a waterfall, so we're driving the GPIOs to drive the LEDs. So that will be in our platform when we program it through USB to the SRAM and then to the SpyFlash, and the SpyFlash is at address 0. So once we have our FPGA Cortex M3 platform in the SpyFlash, then we're ready to go to the software design flow. Now the software design flow is using a lot of the ecosystem of ARM. We used our GOWIN MCU Designer based on Eclipse, which is an open source platform, and we used it for not only our ARM Cortex M1 and M3, but some other RISC-V type processors. But I'll show you how you can use that tool to run the ARM process for your C code that you've written or we wrote in our reference design, and how the compiler and linker can be used to create a raw binary file. And that compiled C code can be running on the platform that we just programmed into the FPGA to make it a micro SoC FPGA. So the bitstream file, the FS file, along with the raw binary can give us a complete micro SoC FPGA solution. So the tools that I talked about that we offer are GNU based, the GOWIN MCU Designer, or GMD as we call it. But there's some other tools out there too, like from ARM. They have a group called Kyle, and they have debugger cables and trace cables, as well as some high level tools that can do compiling and linking that are more elaborate than the open source tools. So those are available, but the tool that we offer, it's Eclipse based, and it runs bare metal designs. So we have non-OS applications. We do have some RTOS available in the reference design. It's based on free RTOS, as well as microC OS 3. So we do have the ability to put a real-time operating system. It's a very lightweight operating system that could be used. So when you do launch the GOWIN MCU Designer or GMD tool, you'll see that we've got a lot of projects, and they're based on our individual peripherals, or there's an RTOS, a microC OS, and free RTOS projects. But the one for our reference design, you could load up and then compile it through the build, put some debug into it, which we already did. So you could go in and turn off the debug if you want to use our reference design for a release. This is the tool that can do that for you. You've got the code editor and the console window. But if you want to create your own project, you could do that by going to the file, pull down, and create a new C project, and then give it a name. Choose the device that you, or the processor you're going to choose, because this same tool can support our RISC-V processors that we have. But in this case, once you choose the ARM cross compiler, then you can have M1 or M3 as your target device. You can include the debug, so this would be the JTAG or serial wire debug, or you can have the run be for release, where you take out the debug, so less instruction code is needed, and less lookup tables in the FPGA fabric. But the other thing too is you want to set the tool chain for the ARM compiler, so you could do that, and then that'll be good for both the M1 and M3 files. So the next thing to do is target which processor. In this case, we've got the Cortex M3. This was the same flow when we used the hard Cortex M3. So whether it's the hard or soft, you can write your code in the GMD builder for the Cortex M3 or the M1, the soft M1. But in this lecture, we're going to talk about the M3. And then the preprocessor, this is the defined symbol that we have to use, the startup clear for the assembler. And then for the include files, the C header files, you have to make sure that it includes the app, the core, peripheral, system, and user. And that's where our C code will be located for the different subsections of our MCU design. The flash linker is where we'll store our raw binary code, and we have the capability to run it on the FPGA, or we could write it to the SpyFlash memory. So once you do the cross linker, it'll take your assembler and C compiler and link them together to create the raw binary file. And that raw binary file will be your flash image starting at address 4000. That will run as your bootloader. We have to make sure we're pointing to the M3, so we do have the M1 option, but in this case, for debug, we want to use the M3 for our reference design. Once again, this could be for the soft M3 or the hard M3 on our 2C and 4C devices. So that's all set up for debug flow. So we hit the build, and this flow would be for a debug flow. So this code will be created, this binary file. And then if we want to download it to the SpyFlash, we have the ability to use the program in the toolbar, and it will launch the same programmer we use to program the FPGA and the FPGA SPY that's attached to it. We can program the starting at address 4000 for the 64 megabit SpyFlash memory that's on the eval board. So you could change this to any device that you'll be using on your prototype board or production board. So once that's downloaded, we have the debug cable. In our reference design, we use the Sager download cable and debug cable. This cable has memory on it, so you could use it, the trace function. And you want to make sure that the binary file is pointed to for debug. And configure the device, the Cortex M3, make sure that the Sager tool knows which controller you're using, and just all the configurations for either it's serial wire or JTAG. In this case, we're going to use JTAG. So once that's set up, then we can run the debugger. It'll download to the eval board, and we could, for debug, do things like breakpoints, single step debugging, reset or run. Once this is in the FPGA and a microcontroller it's running, you'll be able to debug your software code. Here's the cable that is typically used with the tracer cable capability. You have the USB coming in from the computer, and then the JTAG and the two-wire interface going to the board. This flex cable here will be connected to the eval board, and that will use the JTAG to debug the software code. This USB download that we used to program the FPGA earlier and the associated SpyFlash that's on the board can be used for our GOWIN analyzer oscilloscope. GAO is a way to debug and check some of the internal test points, and you could do trigger events on hardware, maybe on some of the peripherals. So you could do a double check for your software code through the disk debugger and verify it in hardware through the USB download cable. So we did the FPGA design flow, got the bit stream, got it into the SpyFlash memory. We did the software design flow, got our raw binary and put it in SpyFlash memory. And we did it on a known working hardware, the development board. You could do the same flow for your prototype board using some of these debug cables. There's not just a Sager, but there's also the Kyle U-Link cable, as well as Lauterbach has some hardware cables, and IAR has cables as well as compiler and linker tools. So that you'll see quite a large ecosystem of support tools out there that can help you debug your design. Along with documentation, when you do the reference install, you'll get, or the reference design install, you'll get a lot of documentation on that reference design, as well as how to debug it. And there's data sheets on our Aurora device or whatever target device you're using. And there's user guides for our GAO analyzer oscilloscope for power analysis. So all kinds of online PDFs we use. You use IP for intellectual property, and then UG for user guides. We've got release notes. So all kinds of documented support, as well as we've got FAEs across the world that can help you with your designs. We've also got eval boards that you can get from our distributors. And I thank you for your time. It's a pleasure for GOWIN and ARM to help you differentiate your products, reduce your costs, and shorten your development time. We're all here to help you implement fast, and hopefully you saw an easy way of creating a simple and instant integration with complete Cortex M1 or M3 onto GOWIN micro SoC devices in your designs. And with that, I want to hand it back to Scott for questions and answers.
Thank you, David, for the presentation. At this time, I'd like to open it up for questions. Please feel free to send us your questions and we will respond here. If we run out of time, we'll respond to you by email. So the first question we've got, David, is what megahertz do the soft versus hard Cortex CPUs run at?
Good question. Usually the soft is running around 50 megahertz, and the hard M3 can run at 100 megahertz because it's an ASIC.
Okay. Okay, we have another question regarding speed. It's how fast in megahertz can the AHB bus run at?
That would probably be the same as the processor. It's about 50 megahertz. The IOs can run at, depending on the device, some pretty high speeds. We can get double data rate on the IOs up to about a gig So 500 megahertz double data rate would give you 1 gigabit of data. But it really depends on the device that you target. The 2A55 has different speed grades, so you might want to choose the fastest speed grade to go faster. And that's where the static timing analyzer will help you. It'll be based on the speed grade that you choose on your device.
Okay, great. Thank you. Another question. Can you repeat, where do I find the MAC address on my computer?
Sure. The PCs have a command prompt that you can go to, your C prompt, and it's IP, the letter I and the letter P, config, CONFIG, space, /all, ALL, and that will give all the Ethernet, whether it's wireless or Wi-Fi controllers that you have on there, media access controllers. So that MAC address will give us the ability to make sure that it's that PC or that license server. We have floating and single-use licenses available. So floating is usually on a server, and single use is on a node-locked PC.
Okay, thank you. Does the hardcore and/or software M3 support DMA peripherals?
It can, but we don't have that in our library. But you can find that in the open source market and add that on as a peripheral on the extension of the AHB or AHB Bus.
Okay, thank you. During the presentation, I saw a DDR3 controller that can be enabled. It can be enabled even in the hard Cortex M3. Oh, can it be enabled even in the hard Cortex M3? What is the maximum speed?
It wouldn't be on that because that's a closed system, but the soft one can run with the I/O that we have. You could run DDR3. I believe it's 103 megahertz, so like 266 megabits.
Okay. Another question. I saw an Spymaster. Do you support SPI slave mode as well?
We do in the FPGA fabric, so it wouldn't be a peripheral. We just have the masters for the AHB bus, but we do have a slave SPI slave peripheral that you could implement in IP core generator.
Okay. Where can I get an evaluation board?
Well, depending on where you are in the world, we have multiple distributors that are either online or have offices. But go to our gowinsemi.com website, and depending on where you are in the world, you can contact one of our stocking distributors that have chips as well as eval boards. But we don't want that to be a hurdle if you don't have any success finding one. We have some that we can loan out or get you in contact with someone that does have inventory.
Okay, thank you. Okay, our last question is any RTOS support?
Yeah, we have two that are included in our reference design. One is Micro C OS 3. The other one is free RTOS. And there's some others that are out there on the open source ARM ecosystem. But those are the two that are lightweight RTOSes. If you want a heavyweight one, you probably have to pay for it, but they are out there. And those can be running on our Aurora family or the Little B family for the M1.
Okay, thank you very much. So as there are no more questions, I'd like to thank everyone for participating in today's webinar. A video will be available starting tomorrow. You'll be sent a link through email to view or download the video. Please reach out to us if you have any additional questions. This concludes the webinar. Thank you, stay safe, and have a great day.